All right, so what we want to talk about is what's called the volume of a solid of revolution. Okay, so this is seems a little bit strange, but it's actually how a lot of objects are formed, especially in manufacturing. So what we do is we start out with a function over some interval, a to b, and so we might have something that looks like this. All right, and what we're going to do is we're going to rotate it about the x-axis, and if we think about that, that's going to form a solid. Okay, because what's going to happen, I'm going to go and let's just look at this part. I'm going to rotate it about the x-axis, and so it rotates around like that. And so what happens, and so you can see like where I just drew, it has a pretty wide rotation, but then in this section right here, it has a pretty short rotation, right? So you can think about forming the border. The border of it's going to be the mirror image. Draw it the best you can. I know it's not going to be perfect, but you're going to end up with the same curve just reflected about the x-axis, and so you end up with this solid that kind of looks like a vase in this case. All right, and so there's its solid. So a basic question is, after you form that solid, is to know what its volume is, and that's what we're going to talk about how to find in this lecture. Now we can explain how to do this with Riemann sums and taking limits of Riemann sums. You can read in a book about how it works that way. But to me, it's a lot easier to understand with the idea of what's called the theorem of Pappus. If you look that up, it's stated a lot more generally where it might not be obvious to see what's going on. But let's kind of take this diagram of what we just kind of what we drew last time. What the theorem of Pappus says is that if I have a solid object, but I can draw an axis through that object somewhere, okay, and we'll call that the x-axis, all right, and if at any value of x along that axis, I can look at the cross section. Okay, so the cross section's like making a slice through it, like that. And if I can describe the area of the cross section at that value of x for every x that's along my axis, okay, so this is the area of a cross section, okay, like that, then what the theorem of Pappus says is that the volume of the resulting solid is going to be the integral between your bounds of integration of your cross-sectional area, dx. Okay, now this is a really general theorem too, but in the case of solids of revolutions, the cross sections are circles. If you look at that picture and think about it, anywhere you move along this axis, if you drew the cross section, you're always going to get a circle. I'm not drawing them very well, but you're always going to get a circle as your cross section. And so we can take advantage of that because we know how to do the area of a circle. It's pi r squared. All right, let's go to the next slide and look at this a little bit more carefully now. By the way, whenever you get to problems, I would highly advise drawing these pictures. There's going to be a formula that seems simple, but using it in a lot of cases can be quite difficult, especially for students just learning this. So again, the idea of the theorem of Pappus, we can use our x-axis as that axis. And so if I want to compute the volume of this object, I integrate from A to B of those cross-sectional areas. Okay, like that. I can explain the role of this dx in a minute. The dx is what's actually giving you volume. All right, but the idea is to help you with the problems is think about picking an x along that axis and looking at its cross section. Okay, so there's the cross section at x, like that. And what we want to do is we want to be able to describe that cross sectional area. Now, whenever we're doing solids of revolutions, that cross-sectional area is always a circle, so it's pi r squared. All right, so now what is the radius of this circle? And so here's my cross-sectional circle right here, and here the center is right there on the x-axis, and so the radius goes from the center up to the top of the circle right there. And so this blue line is the radius at x, okay? And you might want to make sure to realize that the radius differs wherever I am at x, or whatever x value I'm at. Okay, so now what is that radius? Okay, well, it starts at y equals 0 and it goes up to the graph. So that's going to be the function value at x. All right, and so we get this formulation here that the cross-sectional area is just pi times the square of our functional value. Okay, and so then the volume of that solid would be the integral from a to b of pi times f of x squared dx. And some people will write the formula with the pi moved out front since it's a constant, like that. So this is a basic formula, so it looks pretty simple like that, but I can tell you this is one of the harder sections for a lot of students because we get into some trickier problems where you have to do some subtractions and so on. And so don't oversimplify the process, and whenever you see these problems, try to avoid just going straight to that formula. Make sure to look at the picture and make sure you can apply that formula just straightforward. Okay, so now let's see if we can do this though. So we're going to find the volume of the solid of revolution obtained by revolving the given function about the x-axis over the given interval. So let's just start as basic as we can. Let's say we're going to take f of x is equal to x squared over the interval 1 to 3. Okay, like that. So like I say, draw it out. So we have, we're going about the x-axis, so you're going to need some negative side there too. But here we're at 1, here we're at 3. We know that this is the parabola. It increases quicker, but I'm just keeping it on my screen. But the idea is that we have this piece of a parabola right here. Okay, and so I'm going to erase all that to get us a good picture. But we have this piece of the parabola. So there's our function over the interval. And now I'm going to rotate that about the x-axis. And so I'm going to get this kind of thing whenever I rotate, but then we're forming a solid out of that. Okay, so like that. Now again, the more general and good principle to know is that the volume is the integral over your bounds of cross-sectional areas. And if you can start getting that down, we can look at more general problems where the cross sections aren't even circles. Okay, so anyway, to help you here, think about fixing a value of x in the middle of the interval somewhere and looking at that cross-sectional area, realizing that that's a circle. Its area is pi r squared. Now, I forgot to point this out a minute ago. Make sure you realize r varies from x value to x value. If I come over here and look at this cross-section, its radius is much bigger, and so that's why we say the radius depends on x. But in this case, you can see that the radius of our cross sections is just going to be our function value, so it's going to be f of x squared. Okay, like that. And now, a moment ago, I was talking in general, but now we have an actual function, so we have x squared. But then we got to square that too. Make sure you realize you're only squaring the function, not the pi, because the function is what's giving us the radius. Now you got to remember some exponent laws. X squared is x to the fourth. That's a little misleading too. Make sure you realize we multiply those exponents. We're not adding them. All right. So anyway, now we're ready to solve this problem. The volume is the integral from 1 to 3 of pi times x to the fourth dx. All right, like that. And the pi can come out if you want it to. Then we're just we're finding the antiderivative of x to the fourth, which would be x to the fifth with a 1/5 out front. And then this is from 1 to 3. Okay, so now we have pi over 5 times x to the fifth from 1 to 3. That pi over 5 will factor out front of everything. And so then I'm going to have 3 to the fifth minus 1 to the fifth. So 3 to the fifth minus 1 is 242. And so then the volume is 242 over 5 pi. Okay, you can put the pi out to the side or in the fraction. That's up to you. So we got 242 pi over 5. That's approximately equal to 152.05. And if you want to emphasize that there's units, that's a volume, so it's cubic units. And so there would be the volume of that solid. So before we do some more examples, I just want to show you kind of the tie-in to Riemann sums and where the role that the differential plays and how we actually get volume from that. So the way we did this is we said we drew that circle and then we integrated those cross sections, which is perfectly legit. The idea, though, is what you're really doing is you're thinking about forming a partition, and this is one of your xi stars, if you remember from the Riemann sum idea. And so what you're doing is you're actually forming a little disk. People call this the disk method for this reason, or the washer method for this reason. No, the disk method, sorry. Like that. So you're forming a little disk. And so you're getting this disk. It has a circular top, but it has some width or height to it, like that. So that little piece has a volume like that. And so the key thing is there, the volume of that little piece. Well, if you think about it, that's really just a cylinder. If I go and flip that thing over, I just have a cylinder that looks like this. Okay, and so the volume is the base area times the height, like that. And so the base is just the circle, so that is where you're getting that pi r squared. And then, now what's the height? The height is right here in this picture, but it's right here in that picture. If we're thinking about doing a Riemann sum, that height is going to be dx. Okay, and so there's your differential. The differential in that integral is actually what's giving you volume from the area, like that. And so you're getting that pi f of x squared dx. That's actually a volume, like that. And we would call that, just to introduce you to some stuff. Okay, so let's just make sure we have this process down. Now we're back to volume, so we're going to take this curve, y equals 5e to the negative x, and rotate it about the x-axis. And so, and then we'll form a solid. So you may want to pause it here and graph it and see what we're looking at. But if you look at that, now we're only interested from x from 0 to 2. That this thing has a y-intercept of 5 at 0. And if you look at that graph, it just kind of comes down. It's a pretty uninteresting graph, but I also want to show you some stuff about exponents to remind you. Okay, and so now we're revolving this thing around the x-axis. And so this kind of looks like a previous example, solid. There's our solid. And so then we just, to get the basics down, we think about picking any x in my interval, looking at its cross-section. Its cross-section area is going to be pi r of x squared. You don't necessarily need that step, just realize that's what you're using, but the radius here is our function value. So it's going to be pi f of x squared, like that, and so we get pi. Now here's part of it, the reason I did this one. How do we square this? Right here. And so we get pi. Hopefully you see we square the 5, so we get 25. And so now we have e to the negative x squared. And so this is what I told you a minute ago, but it was misleading because 2 plus 2 also equals 2 times 2. But we have an exponent raised to an exponent, and so we multiply exponents there. And so this is actually equal to e to the negative 2x. Okay. And so there's our cross-sectional area. We usually write the number out front. You don't have to. I mean, pi is a number, but you know what I mean. All right, so there's our cross-sectional area. And so now to get volume, we integrate our cross-sections over the interval that we're interested in. And so we would say integral 0 to 2 of a of x dx. And so we have, I'm going to go ahead and move that 25 pi out front. And then we have the integral from 0 to 2 of e to the negative 2x dx. Now you could do a u substitution here. Hopefully you realize there's a composition at the very least. So you can do a u substitution, but this is also just a linear composition. And so if you got that down from previous examples, we know that we just divide by that slope, and so we get over -2. All right, and then an exponential anti-differentiates as itself, and so we're doing this from 0 to 2. We have this constant out front, so we can just keep it out front for our evaluations, like that. And so what are we going to get? E to the -4 minus e to the 0. All right, and so we have -25 pi over 2. Don't let that negative throw you. It's just because of the antiderivative too. We have e to the -4 minus 1. And see, e to the -4 is smaller than 1. And so if you want to make that positive, you can reverse these two around, and that'll drop that negative. If you're having trouble seeing why that's okay, distribute the negative in there, and you'll see that those reverse around. Okay? However you do it, I mean, you could even stop there if you wanted to. Just realize that actually is a positive number. Or you could rewrite it as 25 pi over 2 times 1 minus e to the -4. And that's the volume. Now we just need to approximate it. So instead of pausing, I'm just going to type it in. But you might want to practice with me. Oops. And that comes out to be about 38.55. All right, and those are cubic units. So it seems pretty straightforward. So in terms of if you wanted to give the answer here, I'd give both the exact and the approximate. And you could have, again, you could have used that as your exact answer too. All right, so it seems pretty basic once you see the basic steps, but they get more complicated. And so let's look at some examples of that. So yeah, let's look at a situation where we have a region bounded by two curves. And so we have a region bounded by y equals 2 minus x quantity squared and y equals x. And we're going to rotate that about the x-axis. All right, and then we're going to find its volume. So this, you might want to pause and see if you can wrap your brain about what's going on here. Okay. But the idea here is that if I go and graph those two, feel free to use your graphing calculator if you don't see it. But y equals 2 minus x squared is a downward opening parabola. Its vertex is at 1. And so this is what the first curve looks like. It extends on like this. All right. And then we have y equals x. That's it has a y-intercept of 0 and a slope of 1, so it passes through these 2 points. So I have that really slim region right there. So this is the region that I'm talking about. Now make sure you realize this isn't an area problem. We're not doing area between two curves. But this gives us the region that we're going to talk about rotating. So I'm going to redraw it over here a little bit more stretched out. So 1 and 1. So I have this parabola that opens up, but then I have this line that's straight back there. Okay, now what's the deal? I'm rotating this about the x-axis. All right, and so you know what I'm going to do? I'm going to use a different color for that y equals x there. It might help you see things better. Okay, and so I'm rotating this about the x-axis, and so there's my line being rotated. So I have this part of being a rotation, like that, but then I have the parabola also being rotated, like that, so I have this part of the rotation as well. Okay, so what's happening here is that I have the rotation from the parabola, okay, and so that's kind of making a bowl shape. But since I'm cutting off the bottom part of it too, that hollows it out, and so I'm going to shade that first. All right, so this part that has the red shading is the part that's getting hollowed out. I'm hoping this picture works out right for me. So this is the part that gets hollowed out, but then the outside of that thing is from the parabola getting rotated. Yeah, I guess the red's not going to show up very well. All right, but the point is, the main thing is, I have this solid. It is a solid, but it's hollow in the center, and so so we got to figure out how to subtract out that volume. And I just gave it away basically right there. And so if I want to get the volume of that solid, all right, what do you think I could do? First, I could think about rotating that parabola. And so I get the volume from the parabola, but that's going to be solid all the way through. And so how do I hollow it out? I take out the volume from the line. Okay, now this kind of, you can use some terminology from the area between curve section though. I can think about this parabola as being the top function and this line as being the bottom function. Okay, and at first let's just do this straight from here. Let's just treat this like it's two different volume problems and just subtract the two. But what we'll end up being able to see a concept that might be able to help you. But make sure you realize we're just doing everything from that basic notion that comes from the theory of Pappus. All right, and so for my first region, I'm rotating the parabola, so I'm going from 0 to 1 of pi times the radius in my first rotation comes from the parabola, and so its radius is the parabola's equation squared, or its radius is the parabola's equation, and then I got to square it. So this one's a little bit strange. I have the quantity 2 minus x squared, and then I got to square it. All right, and then I have minus the volume from the line. That's also going to be the integral from 0 to 1 of pi times the line's equation squared. So x squared. Now again, to remind you too, I left some dotted lines in there. Let's see if I can do this. This might get a little tricky. Oh, good. All right, so now where did that x come from? Just to remind you, we're rotating, to hollow out, we're rotating that line. So here's my cross section. So the radius for that inner rotation comes from the line. So its radius is the equation of the line, which is just x. All right. And then remember that dx is important. It gives us our volume. Okay, so anyway, now here's the key thing to notice here before we start cranking away on this. First of all, looking at, well, I'm thinking it as I'm writing here. Okay, we do have the same limits though, so you can combine these two. All right, the thing is, if you think about right here, we have 2 minus x, an exponent to an exponent. I multiply. I raise it to the fourth. A lot of times with polynomials, if you can combine them, it's advantageous to do this combining whenever they have the same limits, because things will cancel or combine, and a lot of times it results in less integrations. The thing is since we have this fourth power here, you don't want to multiply that thing out. We know how to integrate that as a linear composition. And so I would probably keep these ones separate in this problem, but I will tell you it is often advantageous to combine them. Okay, so let me take out a little bit of that. I didn't mean to take out so much. Okay, so anyway, now notice I do have a pi everywhere, so I can just factor it out of the whole calculation if I want to. You don't have to, but I have this pi, and so now I have the integral from 0 to 1 of 2 minus x to the fourth dx minus the integral from 0 to 1 of x squared dx. Okay, and so you might be able to combine those and get stuff to cancel, but I think multiplying out that 2 minus x to the fourth is going to be too much trouble to make that worth it. So I'm just going to do these two integrals separately. But just be aware there are some problems, just like with the area ones, where you can combine that into a single integral. And then a lot of times stuff ends up canceling. So stuff ends up canceling. All right, but just because of that fourth power, I think it's a little bit too much to multiply out. Okay, I'm going to finish this on my next slide. I'm out of room. Now, you may be wondering why I didn't multiply this thing out, because you might be thinking the only way I'm going to get this integral is with the power rule. But if you notice, I have something raised to the fourth, and that's a linear function raised to the fourth. If you need to see that more clearly, Let me get a color where it might be more clearly. This can be thought of as negative x plus 2 raised to the fourth to get that integral. Okay, and so I can integrate this as a linear composition if you understood that, or if you want to, if that never quite sunk in, you would just do a u substitution with u equal to negative x plus 2. However you're going to do it. So now let's find these integrals though. So we're going to get pi times, we have 2 minus x to the fifth, and then a 1/5 out front, but the slope of that linear composition is -1, so I need to do 1 over -1 as well. Okay, and then I can integrate, you can write from 0 to 1 here, and then take the antiderivative over on the right, which is 1/3 x cubed, and then say from 0 to 1. But since these are both from 0 to 1, I'm just going to rewrite it as 1. One place, sorry about that. So I'm going to just take this out right here and close my brackets and just say this entire thing from 0 to 1. Okay, clean up inside that antiderivative part a little bit. Right here, if you think about that, that's -1/5 times 2 minus x raised to the fifth, and then minus 1/3 x cubed, and that's from 0 to 1. Oops, forgot to close my brackets, from 0 to 1. All right, I'm ready to substitute in, so I'm going to plug in the upper limit first. And so I have -1/5 times 2 minus 1 to the fifth minus 1/3 times 1 cubed. All right, and then minus, be careful because we're subtracting several things, so don't forget your parentheses so that you distribute correctly. And then we have -1/5 times 2 minus 0 to the fifth minus 1/3 times 0 cubed. Okay, now that's a 2 minus 1 right there. All right, and so this is just 1 to the fifth, which is just 1, right? So we have pi times -1/5 minus 1/3, because I'm just multiplying by 1. Notice that I have these two pluses right here when I distribute that negative. And so that's going to make that a plus 1/5 times 2 to the fifth. Okay, down here at the end, we're just have a 0, so it's going to go away. And so that's our answer. We just got to get it cleaned up here. And so 2 to the fifth is 32. So I have pi times -1/5 minus 1/3 plus 32 fifths. Right? Okay, so I got to get all these combined here. Notice that my common denominator is, I see I have those 2/5. I'm going to go ahead and combine those. And so now I have 31 fifths minus 1/3. And so my common denominator there is 15. And so it's 15. That's going to be 93 minus 5. Like that. And so I believe that is 88, isn't it? And so we have pi times 88 over 15. And so, long story short, we usually write that. Now, you could write it the way I have it written up above, but usually people write it this way, or they'll say 88 pi over 15. Okay, and so we want to go ahead and get our approximate as well. And sorry about that. And so that's about 18.43. Okay, remember, since we're talking about volume, this would be cubic units. And so there's the volume of that object. So the idea there, I still have some drawing to do, but the idea there is that we had two functions, a top and a bottom function, between two numbers, a and b. All right, and so we rotated the region bounded by them. So we started with this region right here, and then we rotated that. Okay, and so what that did is that created two rotations. There's the rotation from this inner part right here, like that, and then the rotation from the outer part, which is right here, right? Like that, okay? And so if you remember, let's see if we can get a better picture this time. And so if you remember, rotating the inner region actually gives me a hollow space in the middle. So we have the volume of this inner region right here. All right. And then whenever I rotate that outer region, I get the actual volume, the part that hasn't been removed. There, it keeps coloring up. Maybe I should shade in reverse order. All right, let me see if this helps. Doing it this way helps. Okay, so the idea here is I want to take the volume of the red region and subtract out the volume of the blue region. Okay, so that's the idea, but you got to remember where it started from. It started from a top function and a bottom function. All right, and so to get a formula that might help you, like I say, I prefer to do these more just by the concept, but the general concept is that it's the volume from the top function minus the volume from the bottom function. Okay, like that. And let's call this t of x and let's call this b of x for that reason. Okay, like that. And so if I did that, if I did them separately, I would have pi times the integral from a to b of my top function squared. And then I would subtract, don't forget your differential, that's what's giving you volume. And then minus the volume of the bottom one would be pi times the integral over the same region. That's important. B of x squared dx, like that. But see, we have a pi in both of them, so it can factor out. And then also I'm integrating over the same region, and so I can combine them into one integral. And so so you might see this formula right here if you do some reading. Like that. And so very important about this formula, though, people often apply this formula incorrectly. This formula says, remember order of operations, you do exponents first, then you add or subtract. So that formula is saying to square and then subtract. People will often do them in the wrong order. That's not the same as subtracting the two functions like we did with area. Okay, and then squaring. That's not the same. You got to take each function and square it, and then subtract the two functions. Let's try one more just to make sure we got it. All right, here's a fun little random one I thought about. I actually thought the picture would come out different. I wasn't thinking. All right, so we got the region bounded by x equals 0, y equals 5e to the negative x. We've seen that one. And y equals 5 minus 5e to the negative x. All right, so I would graph it to get an idea. You might want to do that before I even carry on. But here we go. And so if you go and graph that, you might want a bigger window just so you can see where your region is at. And so the 5e to the negative x we saw a moment ago, that it has a horizontal asymptote right there. And then if you go and graph 5 minus 5e to the negative x, we actually get something that looks like this. Okay, like that. So whenever you look at these pictures, you want to ask yourself, where do you have a bounded region at? And the important thing to remember too, x equals 0 is part of this. What's the graph of x equals 0 look like? It's the y-axis. All right, and so if you look at it carefully, hopefully you'll see that this region, this little region right here, is what we're talking about. Okay, and so I'm going to just zoom in on that a little bit to draw it a little bit more carefully. But we have this, like that, and then the region that we're talking about. Now be careful, we're not doing area though, we're doing volume. So there's the region that we're talking about. So there's our region R, if you wanted to give it a name. All right, and so now we're rotating that about the x-axis. All right, and so whenever we rotate that about the x-axis, let me see if I can do something a little bit different. Use those colors. Okay, and so here's going to be my first function. Here's going to be my second function. And again, we have that, we can shade that for our region. I'm just helping you recognize the region. But you got to remember what we're actually doing here is that we're rotating these about the x-axis. So this is the part that's coming from my inner rotation. And then this is the part that's coming from, oops, let me get that on there a little bit better. And so then this is the part that's coming from my outer rotation right here. Okay, like that. Okay, and so then you know, thinking concept wise, if I just rotate the top function, it's going to give me all of that volume there in blue. But then I need to hollow it out by thinking about rotating that inner function as well. All right, so let's do this. Well, we're missing something though. So here's my top function. Here's my bottom function. Like that. But what are we missing? Okay, think about setting it up where you're going to say v is equal to the integral of the top function squared minus the bottom function squared. But what's missing right here is we don't have our bounds. Okay, it's pretty obvious that the lower bound is 0. All right, but the question is, what's my upper bound? So we got to intersect those two graphs. And so we'll just come over here, do a little side work. Remember how we find intersections? We set the two equations equal to each other. Okay, this is an exponential equation, so I want to isolate those exponentials. So we have 10 e to the negative x is equal to 5, or e to the negative x is equal to a half. Remember, we take logs to cancel the base of e. So I'm going to take log of both, ln of both sides. All right, so ln over here and ln over here. Ln cancels the base of e, so I just have negative x is equal to ln of 1/2, like that. And so x is going to be negative ln of 1/2, like that. Some of you folks that know your log properties might know that that's ln of 2. You can algebraically simplify those. All right, so we're integrating from 0 to ln of 2, or you could use that negative ln of 1/2 if you needed to. All right, let's see if we have room. I don't want to try to squeeze in too tight here, but the volume here then is pi integral from 0 to 2 of my top function, which is 5 e to the negative x squared, and then minus, oh boy, my bottom function has a lot of excitement for us, doesn't it? 5 minus 5 e to the negative x squared dx. Okay, now what can we do here? Let's I don't see, I think we're going to have to multiply this out. All right, and so we get pi, the integral, I wrote 2 as my upper bound when it should have been ln of 2. We have pi integral from 0 to, you know what I'm going to do? I'm going to pause here and go to the next slide so I can quit trying to squeeze this thing in. So, okay, so here's where we left off, all this excitement here. So we got pi. We just need to get some stuff multiplied out here before we can even start thinking about antiderivatives. So we've already talked about this one. This is 25 e to the negative 2x. Okay, now we're subtracting, but then we got a square. All right, and so if you don't know the squaring formula, just remember you multiply this by itself. Okay, so you have just this times itself, like I said. And so you could distribute it or FOIL it out if you think in terms of foiling. Okay, so we have 25 minus 25 e to the negative x, and then minus 25 e to the negative x, and then plus 25 e to the negative, so we got e to the negative x times e to the negative x. That's e to the negative 2x. Okay. So notice right here, This is minus 50 e to the negative x. All right. And so what all do we have here? We have pi integral 0 ln of 2 25 e to the negative 2x. All right, I need to distribute this negative, so it's minus 25 plus 50 e to the negative x minus 25 e to the negative 2x. Do you notice something nice that just happened there? Looky here. Be careful about canceling. Make sure that you actually have opposite signs that cancel. But those actually cancel each other. And so our integral just became a lot nicer. We have pi integral 0 to ln of 2 of just 50 e to the negative x minus 25 dx. All right, now I just do these two antiderivatives separately. So this is a linear composition right here. And so I just have negative 50. It's 50 over negative 1 e to the negative x, and then minus 25x. That's from 0 to ln of 2. So we just keep chugging along here. We have pi times negative 50 e to the negative ln of 2 minus 25 ln of 2. And then we have our minus from the fundamental theorem, and now we're plugging in 0. Negative 50 e to the 0 minus 25 times 0. So there's another part that becomes nice. That zeroes out. All right, just take it a step at a time. I know it's a little grueling. Okay, now the thing is, exponentials and ln's cancel each other, but we have this negative out in front that's keeping them from canceling right now. But remember how you can handle a negative exponent. You can write it, you can move it down into the denominator as a positive exponent, like that, and now they'll cancel. We'll wait till the next line to do that, though. Then minus 25 ln of 2, there's nothing we can really do about that. And then here, I have these two minuses, so they'll make a plus. 50 e to the 0 is just 1. All right. So we're just cranking along here. We're basically there. It's just this e and ln cancel each other, so I just have a 2 in that denominator. So I got pi times negative 50 halves minus 25 ln of 2 plus 50. All right. I'm not really, well, what's 50 over 2? 25, and I'm subtracting it. So we got pi times 25 minus 25 ln of 2. There's our exact answer right there. Okay? And we would want to then approximate it, which I'll do right now. And so we got pi times 25 minus 25 ln of 2. And that's about 24.10 cubic units. And so there's our volume in that problem. Now, this problem seemed to, well, it was a complicated problem. So, but yeah, so notice it was a complicated problem. The key thing is take it one step at a time, and start out with that picture and figure out what you need to even get started. And then just take it one step at a time, and you can get through them too. All right, I hope that helps.